Welcome everybody to our webinar today. My name is Jill Browning and I will be your moderator today. I can see that we've got a few people in the waiting room that are still in the process of logging in, so we're going to give it just about another minute or so and then we will get started. Thanks for your patience. Welcome everybody to today's webinar. As I mentioned a minute ago, my name is Jill Browning and I will be your moderator for today's webinar, Ensuring Environmental Compliance, Low-Level Metals Removal from Mine Water. Before we get into our presentation today, I do have just a couple quick housekeeping slides to go over. First of all, hopefully you should be able to hear me speak right now, but I do want to mention that should you have any difficulties throughout the presentation today, that there are two different ways to connect to the audio. You can use either the computer audio or call in via your phone line. Also, due to the large number of attendees on today's presentation, we have gone ahead and muted everybody's lines, but no worries, you can still interact with our speakers. And in terms of interacting with our speakers today, you can ask your questions via the questions panel over on the right-hand side anytime throughout today's webinar. And at the end of the presentation, we do have some time set aside for a Q&A session for our speakers to go through and answer that. So feel free to ask any questions that may come to mind, and we will try to get through as many of those questions at the end of the main presentation as time allows. Today's webinar is one of many in our Veolia Water Tech Talks program that is happening throughout the year. If you're interested in signing up for additional future webinars, please feel free to go over and check out the schedule and register at www.veoliawatertech.com. Additionally, we have gone ahead and made available our collection of on-demand webinars that we've conducted over the last few years. So you can access more than 40 on-demand webinars, again, over at that www.veoliawatertech.com. So feel free to go over to the website and browse through the various topics to see if any of those may be of interest to you. One other quick housekeeping note that we have here is a PDF participation certificate will be made available to you at the conclusion of the webinar. You should receive that certificate in your email within probably 24 hours or so. And also at the end of today's webinar, you will receive a quick survey requesting your feedback. We do value and take interest in your thoughts and feedback on that. It should take no more than 20 to 30 seconds, excuse me. And for those of you who do complete that survey, you will be entered into a drawing for a chance to win a $25 Amazon gift card. So if you would be so kind as to fill that out for us, we do greatly appreciate that. Okay, so now I'd like to introduce our speakers for today's presentation. David Oliphant is Vice President of Business Development, Heavy Industries for Veolia Water Technologies. David is proactively involved and responsible for the development and sales activities for large industrial capital projects of water, wastewater, and service solutions. His activities span across all heavy industry applications, which includes providing technological solutions for the mining, remediation, pulp and paper, power, and oil and gas sectors. And also today we have Marc LaLiberté. Marc LaLiberté is a senior process engineer at Veolia Water Technologies with 35 years of experience in water treatment and mining, metallurgy, and heavy industry in general. He specializes in issues of water quality and quantity, treatment of industrial wastewater, treatment of makeup water, and water management. He has focused in the last 10 years in merging seamlessly chemical and biological treatment processes. And with that, I would like to now turn it over to David and Mark.
All right, thank you very much, Jill, and thank you everyone for joining us. I want to wish everyone a good morning or good afternoon, wherever you may be located, and hope all is well with everyone and everyone's staying safe. What I'd like to do this morning or this afternoon is just give you a brief overview of Veolia Water Technologies capabilities here in North America. You know, we are made up of many technologies, both in membrane areas, high rate clarification, which we're going to focus on today, small footprint filtration, standard equipment offerings, really the whole gamut of equipment that we can bring to the water treatment sector. Services, when we look at services, you know, we do have a wide range of services. Looking at our digital platform called Hubgrade, where we work with our clients to develop programs specific on monitoring operations, optimization of plants, etc. So a very customized site service list that we can pull together. Also within our services group as well, we have our mobile water treatment plants, both in process and wastewater, and we will touch on a couple of those today in later on in the presentation. We also have our Hydrex chemicals and full lab capabilities here in North America as well. And the nice thing is these services allow us to wrap up process guarantees on the plants that we're bringing out into the marketplace. When you look at our projects, you know, we have various delivery models, really nothing cast in stone. The big focus is on engineering and procurement of our treatment systems. But again, we have many delivery models that we can bring to the marketplace. Next slide, please. When you look at markets served, certainly today we're focused on the mining sector, and myself personally involved in mining right across North America. But as Jill mentioned before, we're also included in oil and gas, municipal. We look at pharma and food and beverage as more what we call our light industry internal, but also power and pulp and paper as well. So we really do cross all the markets here in North America, and we certainly do look forward to the opportunity to working with you and seeing where we can help you out. And with that, I think next slide, please. So for today's agenda, we are going to look at, again, metals precipitation, low-level metals precipitation in mine water applications. So Mark is going to take over from here and talk about the conventional water treatment plants and how we look at that from an applicable process for metals removal, the principles behind how we're proposing our water treatment facilities. We're going to look at a couple case studies, mine effluent treatment in northern British Columbia, Canada, and talk about how we tackled that specific application. We're also going to touch briefly on a remediation case study as well, where copper and zinc on an abandoned ore spill there. And then we'll wrap up with a conclusion. So again, thank you very much for joining us today. We're really pleased to have you all here. And I will now pass this over to Mr. Mark Leatherverte.
Hello, everyone. Pleased to be with you today. I hope that you'll find this enjoyable. So without any further ado, just do a little intro there. So water treatment mining application, we're focusing today on sites that have to deal with excess water. I understand right now most of the southwestern US is in the draw, but actually we see that we have many locations where there is too much water to deal with, and where that water is contaminated typically by heavy metals, by TSS, the particulate solids and everything, and must be treated before discharge into the environment. We see that the criteria to discharge the environment are becoming more and more stringent. Some of the jurisdiction, obviously it's not the same all over North America, but we see that in some places levels are expected to be in the ppb, the microgram per liters. That's not a lot. What we're going to cover today is two case studies how we can manage to do that. We understand that it does vary from time to time, but I believe that it will give you a good idea of, in general, how we go accessing about that. whoops, sorry, too fast. So what we're looking today is conventional treatment chain for metal removals. It's not the only thing we can do, and as Jill mentioned into the intro, we are also looking at biological processes. Biological processes are not used that much for metal. They're more used for ammonia, nitrogen, or in general organics. We're not covering that today. We have covered that elsewhere, but just so that you know, it is part of the treatment. But today we're focusing on metal removal. How do we go about removing all those metals coming from mining sites? So basically, when we're talking about metal removal, we will be talking about physical chemical treatment, which is basically we'll do something chemically to do a precipitation, and then we'll just use basic physics to have to remove the solids, and that's what we call a physical chemical. That's by opposition to, as I said, biological treatment, which is not covered today. It's simple. It's quite flexible because you have a wide variety of chemical to use. You can be also quite selective depending what you have to remove. You can go there and actually be fairly specific. You will have little or no liquid waste. Normally what you're producing is a sludge. That sludge, on the other hand, need to be handled. That sludge is, because it does contain most of the heavy metals present in the water, that sludge is usually considered to be a toxic waste because of all the heavy metals I remove from the water are now in the sludge. And chemical consumption can be high depending on the water quality and the criteria that we have to meet. It's still fairly simple, and then we can go at surprisingly low concentrations in the treated water if we do our job properly. We select the right equipment, the right chemicals, and that's basically what we're going to see today. So what's the idea there? Metal precipitation. We have something soluble, some soluble metal ions, and then we'll add something else to form solids. That's going to be precipitation. What are the something else? Typically hydroxides. That's I would say that's probably 80 to 90% of the case. Would just basically add caustic or lime or something like that. But can also be sulfides, can be carbonates, sulfates, oxide. There's all kind of plus, not to mention various organic chelatants and things like that. We can also use surface complexation. I'm not going to spend a lot of time on surface complexation because that's a topic by itself, but the idea is that when we add aluminum or iron into water, and then that aluminum salt, that iron salt precipitate, it does form a solid, and that solid has a tendency to absorb many metals. And that's actually the main mechanism that we use to remove oxyanions, such as chromates, molybdates, vanadates, arsenates. All those oxyanions are typically removed using surface complexation. At the end of the day, whether I use precipitation or surface complexation, what I end up with is a solid that contains the metals that I want to remove. So once that's done, we'll go there and I have to remove the solids from water, because it's good to take the metals from the aqueous phase and put that into a solid phase. But at the end of the day, I must now remove my solids from my water. Typically, the main workhorse that we use is something that we call the active flow. Active flow is a clarification process that is based on enhanced flocculation using ballasted floc. What does that mean? That means that we're adding sand, micro sand, into the process. We'll bind the solids that we just produced by precipitation or surface complexation to the sand using a combination of coagulant and polymer. And now we're suddenly going to have solids that are much bigger and much denser also than were before. They will be able to settle very, 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 very fast. And we're talking order of magnitude faster than naturally decanting solids in there. Obviously, all the sands that we add is not obviously, but it is recovered. Basically, what we found is that the sand solid mixture can be pumped and sent to a cyclone. And in the cyclone, the centrifuge force is sufficient to separate the sand, which is recovered, with the solids that we produce, which now make up the sludge. That system, the active flow system, is actually very, very compact, very effective in all kind of conditions, low temperature, high temperature. It's not susceptible to variation in turbidity or TSS. It can also, the flow can vary quite fast. It's actually a system that works very well. There are other systems that can be used from time to time, including multi-flow, which is a system similar but with without the sand ballasted flocculation. But I'd say the active flow system that you see there is probably used in 95% of the mining application that we have in operation right now worldwide. If you look at footprint, and footprint is basically an idea. It's basically a factor of the decantation speed of your solids you form. That actually gives you an idea of the active flow. It's the little rectangle that you have there, compared to a lamella type clarifier, compared to a conventional clarifier. The active flow typically is 20 times smaller than a conventional process. And this is something where we have literally hundreds of applications worldwide. It is very, 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 very effective for that. It does produce quite a good quality effluent, typically much better than the conventional clarifier, because you don't have the issues that you have with turbulence into conventional clarifiers. Where, for example, the sun rising through the day will create a convection current that will give you increase in TSS and so on. You don't have that at all into active flow. So that's probably, as I say, probably 95% of the mine sites where we have treatment plant have an active flow at some point in their process. Let me back up a little bit there. In normal application, up to, I'd say, the 2000s, I'd say active flow was sufficient to meet criteria. But as we said earlier, criteria are becoming more and more strict, more and more severe. And now we have sites where we have criteria, the ppb or sub-ppb concentration. And even if the active flow is actually very good at removing TSS, there's always some TSS, some suspended solid that are present in the water, typically around 8 to 12 milligram per liter. That's not much, but sometimes that's sufficient not to be able to meet the criteria. So what we found is that by combining the active flow with a disc filter, we can actually increase the solid removal efficiency of the system by about roughly a factor 2 to 3. 3 would be pretty typical, I would say. And that reduction in the factor 3, now the TSS going out the SEM would be typically around 3, maybe 3.5 milligram per liter, something like that. That gives you that much more capability to remove TSS and hence to meet your criteria, your total metal criteria out of the system. This filter, it's a system where you have mini discs in parallel. We typically use a filtration, a filter, I mean a 10 micron filter. It's, as I say, it normally reduces TSS from 8 to 12 out of the active flow to about 3, maybe 4, something like that after treatment. It's gravity operation. It is very compact. If the active flow is compact, I think that the disc filter is even more compact than the active flow. Super easy to use. It doesn't produce a lot of backwash, and the nice thing is that if we have a disfilter downstream of an active flow, the backwash from the disfilter can be sent back into the active flow and then will be then further concentrated. So basically, there's no net loss of water out of a disfilter. It is fouling resistant, it is easily cleaned, and it's corrosion proof in the sense that it can be built in pretty much any material that you can imagine. So we can usually find a material that will be suitable for application. Not to mean that every material, every disfilter is suitable for every application, but we can typically design a disfilter to fit. And stuff like chlorides, as an example, are stuff that we do very routinely. That's actually quite easy there. I've covered the basics. As I said, I'm not going to go into much more detail. We do not have a lot of time to go into details. There are things that I went very fast, as I said, like biological treatment, surface complexation, but okay, I think that for now it gives you an idea. I'm going to cover two different case studies. The first one, it's a mine that is in operation in northwest BC. What we're going to show is the results of 3 years of operation. So that's an underground gold mine. It is very remote location. You need to travel over a glacier to actually go there. It's also very limited. The site, if you see in the photo, the site is cut between mountains and a lake, and there was actually very little land for the client to build his infrastructure. So that's actually one of the reasons the client came to us there, because they were really looking at the compact water treatment system and also the discharge limitation, and we're going to show that very shortly. Discharge criteria are very stringent. It is a pristine environment, discharge into Alaska. So there was also the complication that because the watershed actually crossed an international boundary, EPA was involved and everything. So it was kind of a difficult site. So what we went in there, that we went, as I said, with active flow for metal removal, this filter for filtration. We had a breakpoint fluoridation system. The reason for that was because we had the nitrite criteria, nitrite NO2 is that removed by precipitation, and breakpoint fluorination actually deal with that. Capacity is 6,000 cubic meter per day. That's a moderate plant for us, and that's roughly, I'm going to call it at 1,000 gallons per minute there, just for my American colleagues there, just to give you an idea. Metal precipitation using precipitation hydroxides and metal absorbed by surface complexation and this filter. If you look at you've got there various parameters. You have the criteria that we had to meet, and as I said, some of those criteria actually, like 0.1 microgram per liter for cadmium, were actually, or 0.1 also microgram per liter for silver, or 2.5 microgram per liter for lead, are actually fairly strict. Some of the metals, as I said, are removed by precipitation, copper, cobalt, and so on. Some of them are removed by surface complexation. In this case, arsenic, cadmium come to mind. I think that's about it. But anyway, you can see there, that's the influent, that's the effluent out of the active flow. So that's kind of an intermediate step. And then that's the effluent out of the this filter. So in that example that we have there, TSS, an example, are coming at 650 milligram per liter, going out of the active flow at about 6 and out of the disfilter at about 2, which is the pretty typical 3-to-1 ratio. And after that, if you look at most of the solids, it is fairly typical. Sometimes not exactly a factor 3 because there is a residual that is soluble. So obviously soluble go to the disk filter, but you see that typically will go with that kind of a 2-to-1 to 3-to-1 reduction into the system. You will notice that we are passing every criteria there except for aluminum, which is a little bit on the high side, but aluminum was more a wish than a hard criteria. But all the heavy metals like arsenic, cadmium, cobalt, and so on are significantly below the criteria. There were actually most of them probably okay with the active flow, but in this case, the client wanted to be real sure. They wanted to have a safety factor, and then this filter actually give them the assurance that yes, they will be meeting. And even if there is an upset in the operation of the active flow because whatever, some kind of mechanical failure or whatever it is, that this filter is there. It's kind of a catching. Basically, it's kind of a acting as a goaler. They're catching errors or making sure that the client can sleep at night and meet easily their criteria. If you look now at the efficiency of the system, what we did there is made for 7 of the mills a little graph showing what's actually happening. So what you see in blue is what was removed, sorry, in the balanced flocculation in the active flow itself. In red, what was removed with the disk filter, and in purple, what went out into the discharge. If you can see there, we have actually the balanced flocculation, depending on the metals there that we're looking at, balanced flocculation by itself removed between 80 to 99% of the metals, which is already a very, very, very good start into the process. Now, obviously, going back there, some of those lines there, the purple is so small that it's very difficult actually to see. So what we did is that we said, okay, let's remove what's happening into the actual in the balanced flocculation. Let's just look at what this filter is doing, and that's what this next slide is showing. So we can see there that the disk filter actually removes still a fairly good part of what is left after the active flow. And I'd say it's about, depending what, like zinc, maybe a little less, like 20%, but in some places like copper, it's more like 65%. Silver, it's also closer to 65%. Cadmium, it's about half and half. So you can see that the disk filter actually is fairly effective at doing that final polish to make sure that we are meeting the discharge criteria. Conclusion for that case study there, very, very robust performance. The feed war, I didn't see that, do apologize, I forgot about that. Feed war was extremely high in solids. We had feed war repeatedly above 10,000 milligram per liter. That's 1% solids. We're still war. It's not the sludge yet, but I mean, the system operated very, very well, very robust, and achieve very, very low metal concentration that treated war even with that. That's, by the way, a photo of the mill. And then, as said, there's no room. Basically, it's very, very small. That's one of the few mills I know that's actually multi-story. The treatment plant is in the mill, and that mill is actually 3-story high, and it's one of the few water treatment plant that I know that has been built on a multi-story building. There's simply no room. There is no room at that site. Next case study, it's quite a different context. It's a site where we had copper and zinc ore spill, and that's the result of 2 years of operation. So what we had there is it's there's a little bit there. This is confidential, but there is. Let's put it this way: there was an accident and some zinc and ore concentrate was spilled in a waterway in a pristine environment in Ontario. That site was remediated, but the remediation was not sufficient, and then they had to go back and do a final site remediation there. Discharge limits were extremely stringent, much more so than we usually see when we have a mine operation, but that's because of the very pristine nature of the spill. As you can see there on the photo on the right there, remediation of that nature can be quite messy. So what we had to do was actually take all the water there and then treat the water and make sure that after treatment it could be discharged and it would be pristine also as the rest of the site is. So what we have there again, active flow, this filter. In this case, we had also GAC filtration. GAC filtration was required for removal of some of the metals that were forming organo metal compounds. I'm not covering that today, but it's an option we have when we find that because some of the metals have a tendency to combine with organic material to form soluble metals, and obviously soluble metals are difficult to remove. It does happen. It's about the same flow as the other we had. Same basic process. Again, as I said, that's probably 90% of what we do. So metal precipitation using hydroxide and then metal absorption by surface complexation, this filter and GAC filter. So we go there. If you look, same idea there. So we have the various criteria. We're showing stuff where we had no criteria, but it's just still interesting to have a look. And those are average values in this specific instance. So that's not actually that's actually an average over 2 years of operation. So you can see, say it's copper and zinc. We had also a lot of aluminum in the war. Aluminum is not the easiest metal to remove, to be honest with you. And we had the 75 ppb criteria for aluminum, so that one was a little bit difficult to meet there. So you can see that we managed to reduce very significant. TSS, as an example, went from 400 something on average to about 2 on average. And I know that the 2 numbers there, it seems strange because we have a little bit more on this filter than we have on Xflow, but the samples weren't taking at the same time. So we're looking at average of samples taking at different time. Aluminum, huge decrease in aluminum right in the active flow, further decrease into the disc filter. We have, and as you can see there, antimony, arsenic, cadmium also 0.1 ppb, cobalt also 0.1 ppb, and so on. Nickel, zinc, which is also, zinc is not the easiest metal to remove because zinc is also fairly soluble. We went from 4,500 to 31 to 4. So that's almost 8-to-1 reduction into the disc filter. Same thing with copper there. So that was actually a very successful system that we used. We have the same kind of graph there where we can see what was removed. Obviously, aluminum, a lot of the aluminum is, most of the metals in general are removed into the active flow. This filter will remove some, but as you can see there, we go with, in this case, 95 to 99% remove with the ballast flocculation with the active flow system. Again, focusing on the next step because we can't see anything on the previous slide. Just looking now at the disc filter. The disc filter also does remove some metals with fairly good efficiency. Obviously depend on what's the situation. Like antimony in this case is interesting because antimony at that point was soluble. So because it is soluble, this filter will not do anything. But lead and aluminum and zinc as an example are mostly particulate, and then the disc filter was actually quite efficient at removing those metals. So as you see there, except for antimony, because there was no removal, when there are solids in the system, we go there with like 15 to 90% removal using the disc filter. Good performance. Client was very happy with this. It was kind of messy, as I said, like any site remediation there. It's always it's construction site, so you've got heavy machinery there and then a lot of mud, everything. This filter allows us to actually meet the criteria, and without the disc filter, I must say that we've had some upsets in the operation. The disc filter really helped in smoothing those upsets and making sure that we could continue discharging water. The and that gave us a very stable system in a very small footprint. I'm not sure if the picture is very good there, but as you can see, basically we're on the side of a road there, and we had to park. All the treatment system there is basically parked one behind the other, and that's the space we had for doing that remediation. So that's basically, I'm not sure what, maybe 8 or 10 meters wide, call that 30 feet. And that's it. That's all the space we had. And let's say it's extremely small footprint. Yep, that's the space we had. And that's how we operated the system there. With that, Jill, I think I'll passing the
Yeah, thank you very much, Mark. With that, I'm going to open up our Q&A session. We do have a few questions that have come in, but just to remind you as well, feel free to type any questions over in the questions panel. And with that, we will kick off this Q&A with Mark and Dave. First question that we've got here is talking a little bit about the performance guarantee. How is the performance guarantee developed, and do you do various testings with that, or can you talk a little bit more maybe about that?
Yeah.
You want me to go ahead, or you do it?
Mark, I can maybe start off, kick that off.
Go.
And thank you for the question. Very good question. So typically, what we often do, we do have a lot of application experience with various sites that we have, not just in North America but abroad. But in many cases, what we'll do is we have the capability, as I mentioned, at the beginning of the presentation, we do have full lab capabilities. So often what we can do is take a sample of that water into our lab and really give you a clear go, no go as to, how our treatment chain will perform. We've had situations where, if someone's thinking that, well, what if the water doesn't exist? We have had, I think one of the mine sites, Mark, the first one that you presented, we actually prepared synthetic water in our lab to produce various results. So typically what we do is, in many instances, just going in with a jar testing in our lab, we can prepare process guarantees. If we see areas of major concern, we may want to take that a little bit further, whether it be with an on-site pilot or more internal testing. But it really does vary, site by site. But that's typically how we would kick that off. And again, taking our applications experience as well, will give us the confidence to give that process guarantee to our clients to ensure they're going to, meet their regulatory requirements. Hope that answered your question. Anything else, Mark, you'd like to add?
Yeah, I'd like maybe to add, basically at the end of the process, we'll do commissioning, and then once commissioning is done, there will be a test, and the duration of the test, everything is negotiated on every contract. It's not standard. Typically, maybe a week, maybe 2 weeks. I mean, it's very a lot, and then we'll make sure during that test that we can actually meet the guarantee. And if we don't meet, that's where we're actually going to come in and then do whatever modifications are required. And and we'll make sure before we leave that the client actually, that the site we are meeting whatever we said that we would be guaranteeing.
Right.
Yep.
Okay.
Great, thanks guys. I've got two questions that I think kind of go along with each other. First of all is, can this be done with mobile assets? And then kind of the other question that was in here as well is, do the systems come completely skid mounted and ready to plug and play?
Yeah, so again, if the case studies actually that Mark presented here, both of those started with mobile assets. So to answer the first question, Jill, certainly mobile assets play a big part in our mining applications. And I can say, you know, recently the trend has been with a lot of the juniors coming online. You know, the big focus is to try and point your resources at the milling operations, the areas that are going to generate revenue. Typically, looking at what we've seen in the last, you know, 18 to 24 months, is we're doing a lot of mobile applications for metals precipitation, really allowing the clients then to go on a month-by-month basis for their effluent treatment, and you know, deferring permanent installations down the road. And I think that the last case study Mark presented there is a great example of that. We had mobile assets there for the first two and a half years while the permanent facility was being designed, working with a local consultant there. And then after that permanent plant was installed, you know, we pull the mobile assets out. So you know, it really is it's a trend that we're seeing, and typically what we're seeing now is a longer term type application, what we would call a planned you know, treatment. Mark, is there anything else you'd like to add?
The one thing I would keep in mind is that because of mobile plants need to go on the road, there's a limit to how big we can make them. We can have single train that will be up to about 1,000 gallons or 6,000 cubic meters per day, something like that. We can always put two trains in parallel if the capacity is not enough, but at some point in time, if someone come and say, I need to treat, I've got 50,000 cubic meter per day to treat, the answer is going to be nope. Simply do not. The cost of renting and operating, the complication also of operating that many units in parallel doesn't make sense. So at some point in time, you kind of need to go with a permanent system. Permanent system, there's not really a limit to how big they can be. They can be, because we can build them in steel, but if steel it's too small, we can build them in concrete. We can go actually quite large plants there. So that would be a limit to consider when you're talking about a mobile operation. There's a flow above which it no longer makes sense. Am I making sense there, David?
Yeah. Yes.
Great, thanks guys. Another question that we've got here is, how do you recommend to dispose of the reject or backwash?
I can answer that. Basically, it's case specific, and I would tell you we have so many clients. We don't have many clients with the same approach here. Some mines use paste backfill as part, especially underground mines, they use paste backfill. One easy way of disposing of the sludge that we're producing is simply to sand it with the paste backfill, because then it go back on the ground and you forget about that. If you have tailings, the sludge can be disposed of with the tailings. The sludge can be sent into some centrifuge. We actually have a couple applications where we use centrifuge and where we can produce solids at 45, 50%. So they're thickened. Then, as I said, it does contain heavy metals, so it must be disposed of into some kind of cell, something like that. But yes, we can do that. Some of our clients use geotextile bags. That's also a fairly it's cheaper in capex, fairly labor intensive, but we have clients that love their geotextile bags and then use that. Again, the geotextile bag is good for thickening the sludge, but at some point in time it must be disposed of. So typically it would go in some kind of geotechnical cell there for disposal. Uh, Filter press, not that often. We have one or two cases that come to mind where a client wanted to use a filter press to have really a very, very, very dry cake, but that's not something we see a lot. We see that centrifuge have displaced filter press now. Am I forgetting something, David?
No, I think you've touched most of them, Mark. I mean, some you could also say that some clients have the capability of sending that back to their tailings impoundment area as well. I mean, just sending it off to another part of the site that's affected with their tails, combined with their tails. Sorry. So there is that option as well.
That's actually something that we should start thinking early on when we do project design. Very often on the project design, we're focused on how much water quality, how we're going to meet the criteria and everything. But how we going to dispose of the sludge is something that we need to think about early on. And as I said, unfortunately, I'm not sure if it's good or bad, but I mean, it is usually site specific. It's not something where we have a generic answer that is going to satisfy everyone.
Great. I think we've got time for maybe a couple more questions here. Another one that came in here is talking about flow limitations, both on the high and low side for those systems. Are there any limitations there?
Flow turn down is usually very good. So that's for flow turn down. It's for any given unit, but it's still part of the answer is there. Typically, we can go easily 5-to-1 without doing anything fancy. And if we add some recirculation and everything, I can go at 20-to-1 turn down for any single unit. Obviously, if I've got many units in parallel, that increases the turn down, but for any single unit. So 5-to-1 without doing anything, up to 20-to-1 with doing recirculation. Now, the next question is, what's the nominal capacity of every unit? I would say our bread and bar is going to be between, 1,000 and 25,000 cubic meter per day, which would be about 200 to about 4,000 gallons, something like that per minute.
Right.
That would cover probably 90% of the sites where we have installations.
Yeah.
Below that, we have an issue is that, as I said, the active flow requires a cyclone to separate the sand, to recover the sand, because otherwise the sand will be wasted, and the cyclone becomes so small that it has a tendency to plug. So we kind of need to switch technology. And so if someone come and say, I've got the site and I've got 50 cubic meter per day, I don't think the active flow is the right technology. We need to switch technology. Above that, there's, as I say, the range I gave earlier, like 1,000, 25,000, it's pretty typical. But that's if someone come and say, I've got 250,000 cubic meter per day, which is about 50,000 GPM, roughly something like that. Yeah, we can do that. We actually have plants that treat more than that. And if we can build that in steel because it would be too big, we'll just build the plant in concrete. And there's a plant that the US Steel plant, David, is where the Chesapeake Bay, I forgot, I've got the blank on the name of the plant there. That plant is like 200,000 cubic meter per day. So
Yeah.
we can go very big. Did I answer the question, Jill?
And I'm actually at a plant that's producing over 200,000 cubic, industrial plant today that's producing over 200,000 cubic meters per day. It's a concrete facility, but again,
that's basically the size of the treatment plant for a small city layer. At that capacity, you're looking at the city of probably 500,000 people.
Yeah,
It's not that small of a plant. Did I answer the question, Jill?
Yeah, thank you. I think we've got time for maybe just a couple more quick ones here. How is this process, or is it affected by cold water?
Yeah, we're based in Canada. There, that's where the headquarters is. Most of them, not true. We have applications south, but I mean, a lot of our application up north. As long as the water is flowing, it's not ice. There's no problem. It will work. There, it's not affected. Obviously, it must be protected from freezing because freezing will damage the equipment, but the treatment system by itself is not affected by cold temperature.
And I think a lot of that has to do, Mark, maybe just to touch on that, is the fact that it is a ballasted flock, you know, because typically in conventional clarification, it can be affected by colder temperature, you know, and because we develop such a robust flock with the ballast, with the micro sand there, it really, the negative effects of cold temperature are really not seen on a high rate clarification process.
Great, thanks. Just in the essence of time, we'll take one more quick question here. How important is that disc filtration step in meeting effluent criteria?
As I explained, up to 20 years ago, would not have used a disc filter. The active flow by itself is sufficient to meet, if you want, I'm going to call them older criteria, but older, I mean criteria that were established in the 70s and 80s and 90s. The active flow by itself will be able to do that. But as the criteria for some metals of concern have become more and more stringent, we found that no, sometimes you do need to go with some polish. We decide on every case based on what is in the water coming in and what is the criteria going out. We found that with many sites nowadays, we need to go two-stage. We cannot do that with just one piece of equipment. And very often the combination active flow disc filter will be able to do the job. But this is not an absolute. We still have a client site that where we build where we only go with an active flow, no disc filter. It can happen. But I'd say nowadays, especially into new mines that usually have more stringent criteria, that mines that are established and have kind of I've been grandfathered in with the less stringent criteria. I'd say that, David, 80% of our recent mine sites have been using the combination of active flow and disc filter.
It's really becoming the norm versus the exception, for sure, for sure.
Great, thank you guys. Thank you both very much. And with that, that will conclude our presentation today. I do apologize if we did not get to your question, and we will follow up directly with you afterwards. Also, just a quick reminder, we do appreciate if you do take that quick survey at the end of today's webinar. Again, should take no more than 20 to 30 seconds of your time. And for those of you that do, you will be entered into that chance to win a $25 Amazon gift card. So with that, I do thank you very much for taking time out of your day. This presentation has been recorded, so we will send out a copy to you within the next 24 hours or so as well. And with that, feel free to check out any upcoming VeoliaWaterTechTalks.com, again, over at that www.veoliawatertech.com. And thank you guys very much. Thank you.
Yes, thank you for your time. We really appreciate it. Stay safe, everyone.
Thank you very much.